Hello everyone, myself Nabinta Deimari, Assistant Professor, Civil Engineering Program, Assam Downtown University. Today I'll be talking with you about the pre-stressed concrete beams with eccentric tendons. In the last classes, we have discussed about the pre-stressed concrete beams with concentric tendons. That means which have no eccentricity, but the tendons are placed at the center of the beam. So let's go and check out what are the eccentric tendons and how we can solve. We will take a problem on eccentric tendons too. So without wasting time, let's go further. So if you see here in this figure, this is a simply supported beam with a UDL, dead load, and any other loads, or maybe only the dead loads. So this is the center, this is the CG of the beam, and this is the tendon here. This is your tendon. This portion is your tendon, which has, okay, this tendon will have an eccentric, this tendon will have a pre-stressing force P here as well as here. Due to the pulling, we will have a pre-stressing force in this way. So these are your pre-stressing forces. So that means what? This is your CG and this is here. So this is called the eccentricity. This distance from the CG to the tendon is your E eccentricity. This distance is known as your eccentricity. So now the basic principle of this is that the stresses on this section, which will consist, this is a simply supported beam of UDL given here, and our tendon is placed here somewhere at the bottom below the CG, and this is the which is known as the tendon is placed at an eccentricity. Now due to this eccentricity, there will be three types of stresses. Earlier there were two types of stresses. When your tendon was concentric, that means on the CG, your tendon was on this line CG or the center of the beam. So in that case, we had at the midspan, we had two stresses, which was stress due to this pre-stressing force P, and the stress due to this bending moment due to this load. Due to this load, whatever was the bending moment, due to that bending moment, there were stresses developed. Those two were the stresses. But now, due to this eccentricity, another stress will be developed due to this eccentricity, because there is a moment, there was moment due to this load, due to dead load or live load. Due to the loadings, dead load, live loads, there were moment. Okay, that moment was in this way, plus that means compression at the top, and minus, that means tension at the bottom. Okay, due to this load. Okay, so now due to this eccentricity, there will be another moment, which is, that moment will be how much? P into this E. That moment will be P into E, and therefore that moment is in this way, because your tendon is below the CG, so your this thing is, your moment is going to come in this way. Okay, so that means your tension up, and at the bottom will be compression. Okay, so due to this, that means what I want to say basically is that when you have an eccentric tendon which is placed below the CG, what happens? You have three stresses. One is your direct stress, then another one is the stress due to eccentricity. Due to this eccentricity of the tendon, there is one stress. Another one is stress due to bending moment. Now we know that the direct stress is how much? P by A. This direct stress is P by A, which is uniform throughout the section of the beam. It is at the top, it is same. It is same at the bottom, at the sides, everywhere it is same, uniform. So it is direct stress. Now the next one is stress due to eccentricity, which is minus plus PE by Z, which I told you now. This one minus and plus. Due to this eccentricity, there is a moment P into E. P into E. So therefore, we have a moment due to this uh, pre-stressings of sorry we have a moment here due to this eccentric loading. Due to this eccentric loading, we are having how this tendon is going to bend in this way. So that means what? there is eccentricity, this moment is there, so my negative here, positive here at the bottom. So, and also another third stress which is developed is stress due to the bending moment, which is given by m by z due to this load plus minus m by z. That means at the top it is compression, at the bottom it is tension. So therefore the stress at the extreme top will be how much? P by A minus PE by Z plus m by z, and we have at the bottom it will be how much? P by A plus PE by Z minus m by z. So these are your, this is the basic principle of eccentric tendons. Now if we go and check out one problem, you can see this. Before we go to the problem, these are the stress diagrams. This is a simple cross section of a beam, and we have a direct stress will be there due to the pre-stressing force P by A, which is uniform throughout. Then we have the stress due to eccentricity PE by Z, which is minus plus, it was so minus, that means it is, earlier we used to take the stress due to bending moment was plus minus, that means compression at the top, and so on the right hand side we used to draw the stress, and on the tension will be on the left hand side. But here in this case, the stress due to eccentricity, we have the tension at the top, so it is on left side, and on the right hand side we have the compression representing in the stress diagram. So the total stress will be how much? P by A plus, sorry, minus PE by Z plus m by z, and at the bottom we will have P by A plus PE by Z minus m by z. So this will give you your total stresses. So when we take a question, now if we take this question, here the dimension is given to us 400 into 600 in section, and it has a span of 6 meter. It has a dead load or life load of 16 kilonewton per meter and a pre-stressing force of 960 kilonewton. So here this is the diagram. That means here you have the centricity. Here this is your eccentricity, E is 100 given already in your question. You have your pre-stressing force 960 kilonewton. The loading is given to you 16 kilonewton per meter. The total load span is given to you to be 6 meter. We have an eccentricity of 100 So now if we try to solve, we have to calculate what is our question. Determine the extreme fiber stresses in the concrete at the midspan section. That means somewhere here at the midspan section, we have to calculate the top fiber stress and the bottom fiber stress. So to find out, we know what this in this here we have an eccentric tendon. So there will be three stresses developed, which is the stress due to this pre-stressing force, stress due to this moment which is generated due to this load, then the stress due to this eccentric tendon. Due to this eccentricity there is a moment, and due to this moment there is a stress which is minus plus PE by Z. That means three stresses are developed. So we area we can calculate 400 into 600, which we got to be 2.4 into 10 to the power 5 square. Then we can calculate the z will be how much? Bd square by 6, and bd we already know the dimensions are given to us. Next is p, we know plus minus p by a, sorry, P by A, P is 960 kilonewton, area we know, P by A. The first stress we can calculate, which is the direct stress, P by A. Then the next stress is our what? Stress due to this bending moment. Now the bending moment due to this load will be how much? This is a UDL of 16 kilonewton per meter. That means if we calculate the moment here due to this load will be how much? M is equal to our W L square by 8, WL square by 8. So we can calculate the moment, and therefore due to this moment what will be our stress? Plus minus m by z. M we know, z we will know, bd square by 6. Z is equal to b d square by 6. So we can calculate this bd square by 6, and then the third stress which will be there will be what? Due to this eccentricity, so that is minus plus PE by Z. So P you already know, eccentricity you know 100 and Z you know already know. So and the total stress will be how much then? We know it is this one, P by A minus PE by Z plus M by Z at the top, and at the bottom P by A plus PE by Z minus M by Z. So if we go to the solution here, we will see what? Here you see the Z is BD square by 6, this much, 2.4 into 10 to the power 7, it comes out to be this much. Then moment we know WL square by 8, and we got it to be 72 kilonewton meter. Then the direct stress we know how much it is P by A, and it is calculated to be 4 Newton per mm square. The extreme stress due to eccentricity, direct stress, the stress due to eccentricity is minus plus PE by Z, and P we know 960 kilonewton, then E we know, Z we know. So this stress due to eccentricity comes out to be minus plus 4 Newton per mm square. The stress now due to the external bending moment, the last one comes out to be plus minus m by z, which is m we already know, calculated here 72 kilonewton meter, and z also we know. So this stress comes out to be plus minus 3 newton per mm square. So therefore what will be our final top stress? Our final extreme top stress will be plus 4, minus 4 and plus 3. That means 4 minus 4 0 plus 3. So therefore our top stress will be 3, and at the bottom it will be how much? 4 plus 4 minus 3. So 8 minus 3, if you go, it is 5 Newton per mm square. You can see here. So the top stress is how much? We got correct, 3 Newton per mm square, and the bottom is 5 Newton per mm square. So this is the stress diagram. After calculating the stresses, you can draw the stress diagram where this is the basic cross section. Then we have the stress due to this direct pre-stressing force. Due to the pre-stressing force, the direct stress is 4 at the top and the bottom, same uniform. Then we have the minus plus PE by Z, which we calculated to be 4, this one, PE by Z minus 4 PE by Z, so minus 4 plus 4 at the bottom, and the M by Z was calculated to be 3 plus minus 3. So that is plus 3 compression minus 3 tension. So at the top, now the total stresses will be how much? 4 minus 4 0 plus 3, so 3 Newton per mm square, and here plus 4 8 minus 3 5 Newton. So that means we can see this is our final stresses on the this particular beam of the question. So we can see the entire beam is under compression at the top and at the bottom. Only the difference is at the top we have the stresses little bit lesser than the bottom. At the bottom we have more stresses developed due to this loading and eccentricity of the beam. So yeah, this was your solution to a eccentric tendons. Thank you. We will meet in the next class with a different bend tendons. We are going to discuss the bend tendons. So for now, thank you so much.